Hey guys, today's lesson is complex numbers and is found in section 2.4. We're going to use the imaginary unit I to write complex numbers. We're going to add and subtract, multiply complex numbers. We're going to use complex conjugates to divide complex numbers, and we're going to plot complex numbers in the complex plane. All right, so the imaginary unit I. Some quadratic equations have no real solutions, such as x squared plus 1 equal to 0. Mathematicians created an expanded system of numbers using the imaginary unit I, defined as I equal to the square root of negative 1, where I squared equals the square root of negative 1. So by adding real numbers to real multiples of this imaginary unit, you obtain the set of complex numbers. Each complex number can be written in the standard form a plus bi, where a is the real part and b is the imaginary part. So the first thing we're going to do is we're going to add and subtract these complex numbers. All you need to understand is that you are truly just using combining like terms. That is it. So the like term that matches with our not our coefficient, but our constant 3 is 2. So 3 plus 2 is 5. All right. Then the number that matches with, or the term that matches with negative I is 3i. So negative I plus 3i is 2i. So our answer is 5 plus 2i. All right. On this one, nothing matches with negative 4, so it is still our real part. And then 2i and negative 2i match together, but they are opposites. So our answer is just negative 4. Let's keep practicing. This one, what I'm going to do is, because there are so many terms, I want to write them all out. In the first one, what you should notice is that the negative is going to distribute into the first set of parentheses. So this is going to leave us with 3 plus 2 minus 3i minus 5 and then plus i. So let's add up all our constants. So that's 3 plus 2 is 5, minus 5 is 0. So all of those are gone. And then we have negative 3i and positive I. That leaves us with negative 2i. All right, on the second one, again, I want to distribute that negative. So in the end, our answer, I want to write it all out. We have 3 plus 2i plus 4 minus I minus 7 minus I. So the constants that work together are 3, 4, and negative 7. So 3 plus 4 is 7. 7 minus 7 is just 0. So again, all the constants once again are eliminated. And then 2i minus I leaves me with 0. So our answer actually is just 0. Okay, now we're going to practice multiplying our complex numbers. All right, so the first thing that I want to do is multiply I times negative 3i. Just thinking about I as just a regular variable, this leaves us with negative 3i squared. But our rule earlier said that I squared equals negative 1. So if I rewrote this, this would be negative 3 times negative 1, and so our answer is just 3. Okay, on the next set, the square root of negative 4 is actually, because we know that I equals the square root of negative 1, then I can say that square root of negative 4 coming from negative 1 times 4 coming from negative 1 times 4, okay? This portion here is going to leave me with 2i. And if I follow the same rule with the other one, that's going to give me 4i. Square root of 16 is 4i, or negative 16 is 4i. So 2i times 4i is 8i squared. And again, just like our last problem, I'm going to multiply 8 times negative 1, so our answer is negative 8. All right. Let's keep multiplying. This first one is a binomial, so I'm going to put it in a box. It's a little bit easier to see everything. So this is 2 and negative I, and then 4 and 3i. So that'll leave us with 8, 6i, negative 4i, and negative 3i squared. However, negative 3i squared is really negative 3 times negative 1, which is positive 3. All right, so adding on the diagonal, 8 plus 3 is 11, and then 6i minus 4i is 2i. So your answer is 11 plus 2i. On the second one, again, we're going to use a box to help us see this just a tad better. So this would be 3 and 2i, and then 3 and negative 2i. So this is 9, negative 6i, 6i, and negative 4i squared, which is really negative 4 times negative 1, which is really 4. So again, your real number is 9 and 4, which gives you 13. And then this time the i's are going to cancel, so our only answer is 13. Our last one, we have 3 plus 2i squared. Understand that 3 plus 2i squared is the same thing as 3 plus 2i times 3 plus 2i. If you just distribute your squared inside, that is wrong, okay? That does not work. So if we create a box, this is 3 and 2i, and then 3 and 2i. It leaves us with 9, 6i, 6i, and 4i squared. 4i squared is really the same thing as 4 times negative 1, which is negative 4. So again, adding your like terms, 9 and negative 4 will give you 5. And then 6i plus 6i is 12i. So your answer is 5 plus 12i. All right, the product of two complex numbers can be a real number. This occurs with pairs of complex numbers of the form a plus bi and a minus bi. And so in other words, these two are actually they're opposites of one another. Only the b term is opposite, not the a. The a's are both positive, or they stay the same. And again, these are considered conjugates, so complex conjugates. And specifically, we use complex conjugates when we are trying to eliminate a denominator, because technically a denominator is not simplified fully if it has a radical, or in this case, if it has a imaginary number in its denominator. So the conjugate of 1 plus I is 1 minus I. So we're going to multiply by 1 minus I over 1 minus I. Now the numerator is pretty straightforward. If I distribute my 1, I get 1 minus I for my numerator. For the denominator, however, we need to go ahead and use the box to determine it. So that's 1 in positive I and then 1 in negative I. 1 times 1 is 1, negative I, positive I, and then negative I squared. Negative I squared is really negative 1, which is 1. What is going to happen is that 1 plus 1 will equal 2, and the i's will cancel. So this is our final answer because it is now simplified. So 1 minus I over 2 is our simplified answer. And again, we had to use conjugates, which in other words is the opposite of your b term, right? So if 1 plus I was the original, then we just changed the center integer to negative, okay? Let's try another one. So for 2 plus 3i over 4 minus 2i, again, we multiply by the conjugate. So the conjugate for this one is actually 4 plus 2i over 4 plus 2i. And I really need to specifically say the conjugate itself is 4 plus 2i. So yeah. Anyway, we need to go ahead and multiply. Now this one isn't just a distributive property. So we're going to have to do a box for the numerator and a box for the denominator. So here's a numerator and here's the denominator. That's really off, but okay. All right, 2 and 3i, and then 4 and 2i. 4 times 2 is 8. 2 times 2i is 4i. 4 times 3i is 12i. 3i times 2i is 6i squared, which is really 6 times negative 1, which gives us negative 6. So if I combine like terms, 8 and negative 6 will give me 2, and then 12i plus 4i is 16i. So that's my numerator. Let's check on the denominator. That's 4 and negative 2i and 4 and positive 2i. That's 16, 8i, negative 8i, and then negative 4i squared. Remember, I squared is negative 1. So negative 4 times negative 1 is positive 4. The i's cancel. They should, because that's the whole point of doing a conjugate or multiplying by a conjugate. And again, 16 plus 4 is 20. So as a fraction, we are left with 2 plus 16i over 20. However, that's not our final answer because each term can be divided by 2. So our real answer is 1 plus 8i over 10. All right, let's keep going. Complex numbers. So complex numbers are used heavily in fractal geometry. These numbers are found on a coordinate system called the complex plane. In this figure, note that the vertical axis is the imaginary axis and the horizontal axis corresponds to the horizontal axis is the real axis. So the point that corresponds to, that's supposed to say to, the complex number is a plus bi, which is technically a. Now, there's no diagram, obviously, but let me go ahead and draw it. Essentially, your real axis is your x-axis, your imaginary axis is your y. So if we were to plot a point, this ordered pair AB comes from A plus BI. All right, so let's just practice graphing. I'm going to follow these graphs on the same graph. So what that's going to look like for us, so if I see 2 minus 3i or 2 plus 3i, that really, and if this is the real axis and this is the imaginary axis, this really corresponds to 2, 3. So I go to the right 2 and I go up 3, and that's my first ordered, that's my first complex number graphed. The other one, negative 1 plus 2i, actually corresponds to negative 1, 2. So negative 1, 2 is here as a complex number. The third one, 4, well, 4 is actually our real number, but we don't have an imaginary, so it's just going to be out here. And then our last number, negative 3i, it does not have a real number component, but it does have an imaginary, so we would just go down 3. And so that's how we would graph them. Truly, 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 you should graph them on different graphs each time, but I just did one because I knew I wouldn't have much space. So anyways, guys, we are done. If you have any questions, again, please come see me for tutoring.